Let's let's move on to this new sector, bioenergy sector, and the mitigation potential in doing this and some co-benefits. Bioenergy is already being used for heating and cooling, and there are ways to increase efficiency there. Bioelectricity, biofuels for transportation, like ethanol, for example. Combined heat and power systems, which is similar to increasing efficiency in the heating and cooling systems, and we'll see a schematic of how that is done. Biomass energy with carbon capture and sequestration, or BECCS, which is a big part of the portfolio for the future in terms of mitigation potential in the IPCC AR5, and most likely to be the same in IPCC AR6, which should come out soon as well. So this is a bioenergy options and core products schematic showing the various types of biomasses, the processes involved, and the energy carriers involved, and some byproducts involved as well. And you can see a dedicated lignocellulose production system, which is a kind of way of reducing biomass loss by using the entire cellulose, which is a large part of the body mass of the trees, which are typically not used in conventional bioenergy, which tend to focus on the seeds or the leaves and not the whole body. Okay, so nonetheless, you end up with residues even when you use conventional commodity crops like sugarcane and sugar beet, cassava, wheat, potato, barley, maize, and oilseed rape, and soy and palm, and so on. So you end up with lignocellulosics, undifferentiated biomass. On this side, you have processes like fermentation, biochemical conversion, could be pyrolysis, methane, esterification, anaerobic digestion for producing methane. And then you have the energy carriers and byproducts here as well. The processes here, thermochemical conversions, pyrolysis, as I mentioned, gasification. We will see the so-called synthetic fuels are produced by this, the syngas that's mentioned here, bio-oil like biodiesel as well, and the Fischer-Tropsch process, which converts to bioenergy as well. Biochar and platform chemicals, food and feed, for example, proteins, and biochemicals are the byproducts, and the energy carriers are hydrocarbons, electricity and heating and cooling, biodiesel, bioethanol, biobutanol, biomethane, and so on. Okay, very well. How does it add to the mitigation potential? Obviously, if you do life cycle analysis and make sure that the energy that is produced is actually not producing more greenhouse gases than the energy equivalent that is coming out as biofuel. That's the key, including the transportation, etc. Okay, combined heat and power, and combined heat heating, cooling, and power are systems like this, where fuel and water are going into a turbine or an engine, and there is a exhaust gas heat recovery unit that goes into providing steam or hot water for cooling and heating, and that is supplied to building or facility or the grid. So it depends on whether it's a utility scale or consumer scale system. In this case, there is a boiler which is directly producing steam to drive the generator, and also doing the similar loop here for steam and hot water for building or the grid in terms of heating and cooling. Okay. What is the point of combining heating, cooling, and power? Basically, when you look at just conventional systems of power plants providing electricity and boilers being driven separately for steam and hot water, the efficiency of the system is about 50%. Whereas when you combine the heat and power systems, you can up the efficiency to almost 75%. That is a massive increase in efficiency. Okay, obviously can combine well with the bioenergy and of course with bioenergy and carbon capture and sequestration. This tends to wants to avoid emissions at all, especially at source if the capturing is done. Of course, there are issues about where to store it or how to use the CO2. There are many uses for CO2 as well, like enhanced fuel recovery that we'll see here. So you have the atmosphere, and photosynthesis is taking up CO2, which is what is producing the hydrocarbons and the biological storage that we are considering here in the land biosphere system. And that biomass is being fed to a power plant. Maybe there is also some fossil fuel that's combined with it, let's say to avoid what is called dispatchability, or ramping up production when there is a demand because of midday heat or heating requirements in a winter storm and so on. That power plant is obviously going to produce CO2, and that can be used in a chemical separation system to separate out the flue gas with the membrane and separate out CO2. And that CO2, some of it leaks out, but it can be used for underground storage, like a geological storage for a long time. There are issues in terms of perturbations, but all evaluations thus far say that storage of CO2 doesn't seem to induce earthquakes as far as we know so far, like hydrologic fracturing or fracking to extract oil, shale, and so on. Includes some little explosions, which is actually causing what are called micro earthquakes. That doesn't seem to be the case for CO2 sequestration. And there is potential for negative emissions with storage if this is done properly. And CO2 is also used for enhanced oil recovery by pumping CO2 to push out the remaining oil that is not easy to just suck out by the drilling process, especially when there are horizontal channels to be emptied out, either by fracking or by pumping CO2 and water into the oil wells. Okay, there are additional arguments that these things are basically going to create employment for people who are already trained in the oil and gas industries. This is just another schematic of the BECCS, so energy crops, high biomass yield, extensive availability, and one has to worry about biomass residues for sustainability as well. So CO2 is captured naturally there. Combustion, fermentation, aerobic digestion, gasification, etc. And there is CO2 capture for geologic storage in saline aquifers or depleted oil and gas fields, again potentially creating employment for people who are already in that business but maybe underemployed or unemployed because of the depletion of the that particular oil well. Fuel upgrading, gas cleaning, and liquefaction. So you produce energy products there. Heat, biohydrogen, biomethane, synthetic biofuels, which are intermediaries to usable fuel in the next step. Electricity, and then there are non-energy bioproducts as well. This is just additional thought on how biomass can be combined with the solar energy. So of course producing hydrocarbon is solar energy. Leaves are basically solar cells which are taking solar energy, capturing CO2, combining it with water and sequestering carbon, right, and producing energy in terms of hydrocarbons, which serves existence of all life forms. So there is the biomass, and there is direct photovoltaic and wind energy, and there are bio-inspired processes like catalytic split to produce hydrogen from water and so on. And of course we still continue to use fossil fuels. Biomass then goes into carbohydrates, oil, syngas, and heat electricity. So electrolysis is used in some cases to produce hydrogen. So hydrogen is very efficient fuel. There are rumors of how dangerous it is, but it is argued that it is no more dangerous than a regular fuel tank. But producing it at scale is still something that is being worked on in terms of meeting the fuel demand, let's say, for just the transportation sector. Okay, so there is again hydrogen. This is the Fischer-Tropsch process of converting syngas into diesel that I mentioned before, and that drives the bioeconomy and so on. So this is just a schematic, but in the other course that I have recorded on Bending the Curve, there is a chapter on the technologies emerging in the energy sector, and one of them is how to combine renewable energies with conventional energies and hydrogen as a battery that's available to fill the gaps when there are intermittencies in wind and solar. So solar and wind are not continuous sources like fossil fuels or biofuels, so you need something to fill the gaps when there is an increase in demand and dispatchability or on-demand supply of power has to increase. Okay, let me just add biochar here as well. Biochar is a process that's shown here schematically for all its benefits. So reduced methane soil emissions, reduced N2O emissions, carbon capture, carbon negative energy balance, and reduced odor. Let's say from forest fires. So this is viable and sustainable, has many soil benefits as well for health and functionality, decreased nutrient runoff because the property of the carbon. Biochar is basically something that is produced partially decomposed, partially reduced biomass. So that's biochar, which can go into soil, and here it's being shown for reducing pollution, runoff, etc., which I won't get into, but you can look at that here. But coming back to this, that biochar put on the soil increases the carbon content of the soil, which is very useful for increasing yields in addition to sequestering carbon. This is already demonstrated. So the increased soil carbon, there is a good feedback between soil carbon and soil water. The water holding capacity goes up, so that is what is meant here also as decreased runoff, improved soil fertility, that's what I meant by increased yield, and improved soil tilt, the ability to plow it and so on. Okay, so biochar is now also being done at commercial scales and profitably, so they are it's a very useful thing. It is also shown to be have the ability to remove contaminants like heavy metals, organic contaminants, etc., because of the adsorption properties of biochar. Carbon in the soil is very beneficial. Lots of co-benefits in addition to the carbon sequestration potential that we are looking for here. Okay, so that's a quick run through the bioenergy sector and the pathways for mitigation of climate change through the bioenergy sector, in addition to producing energy in a renewable fashion if it's done well. So you sequester carbon into biomass, you use biomass to produce energy, and if you avoid additional emissions, then you can make it completely carbon neutral or carbon negative as is suggested here.